Hello, I'm Kay Suarez.
And I'm Nick Bell.
And today we'd like to talk about Anacin-X, our framework to capture non-determinism in MPI applications. But before we get there, I want to discuss the background here, which all stems from an assumption. Computers do exactly what we tell them. That is generally correct. But the intuition that comes from this is that program execution is identical for the same input. In reality, what we have asked Chpc code to do especially is to be asynchronous for scalable performance. This asynchronism means that program execution can vary on the same input. This variation is called non-determinism. Multiple types of non-determinism exist, but we're focused on MPI point-to-point communication non-determinism. So just to motivate why you care about non-determinism, I want to show a couple examples. One on the left is an expensive bug. It is in the software Hyper, which solves linear systems of equations. In this, there was a non-deterministic catastrophic bug which occurred in only 2% of executions. And if it were possible to run this quickly over and over, that wouldn't be too bad, but it took a couple hours for this bug to actually manifest. The impact of this? It took 18 months of scientists' time and almost 10,000 node hours to get enough data to debug the problem. And then, let's say the software doesn't crash, you could have variation results, such as on the right in ENSO. ENSO is a software that detects galactic halos to look at creation of galaxies, formation. And in this particular case, the detection of galactic halo number 49, not present on the left, present on the right, is non-deterministic. This harms the trustworthiness of the result because if there can be a fading in and out of detection, who's to say that any of the results are correct? Of course, with such a large problem, there are already approaches in the field to deal with this. One is record and replay, which just records an execution and then can run it the same way again. A tool you might know of that does this is Rempi. And then another method is motif detection. We have a pretty good idea of a bunch of classic ways that non-determinism manifests like this. So tools like Sabalon just go ahead and document all these ways, and then when run on application, will detect where that sort of repeated problem is. And then there's crash debugging, debuggers, and some are even specialized for a specific problem, like PopMine, which finds the cause of a software crash that is non-deterministic. However, these methods have weaknesses. In record and replay, you've determinized an execution, which is the point, but let's go a bit deeper into that. You've lowered your understanding of the application because let's say you have a simulation with a high dimensionality of input. The recorded execution is for one input set. Therefore, in the end, you end up only understanding one input. If a user does a different input, it could fail in a different way, or even the same way, and the bug was never actually fixed. In the field of motif detection, you're limited by existing knowledge. You have your trained set of motifs, and if a new bug happens outside of that, you have to spend those months the Hyper team did getting in that new motif and understanding it. And then when you're just doing crash debugging, you ignore the root cause of non-determinism, just fix the last mile, and you're restricted to catastrophic manifestations. You can't handle ENSO. So we aim to supplement this with Anacin-X, which explores rather than suppressing non-determinism, running an application normally. We quantify non-determinism between multiple executions, removing this need for prior knowledge. And then we reveal root causes of non-determinism in even non-crashing applications, meaning that applications like ENSO will have a tool they can use to handle this problem. So, as for how we do this, I'm going to pass it off to my colleague, Nick Bell.
All right, thanks, Kay. To do this, Anacin-X as a framework is broken up into four main stages. The first stage traces an input MPI application, along with some input parameters that are outlined in previous publication of the authors listed at the bottom of the slide. The tracing stage generates traces and collects the traces using three tracing tools. This stack of tools, SST-Dumpy, Pluto, and CSMPI, produces many trace files that encode a lot of data about the input application. And CSMPI, in addition, allows us to find call stack data, specifically We can identify functions that correspond to non-determinism at different points of the execution. In the second stage of Anacin-X, we use dumpity graph to take all the trace files and build a graph structured model of the data hidden in those files. We call this graph an event graph. The graph model allows us to perform mathematical operations and apply mathematical tools to the data. Specifically, in Anacin-X, we apply kernel calculations to the event graphs. And in this third stage of the Anacin-X framework, the kernel calculations are used to provide a proxy metric for the similarities between the event graphs and correspondingly the similarities between the runs of an application. Finally, in the fourth stage of Anacin-X, it comes packaged with tools for visualization and analysis of the data encoded into the kernel calculations. Along with the 4 stages of this framework, Anacin-X comes packaged with 3 Chpc communication pattern benchmarks, specifically the message race benchmark, the AMD 2013 benchmark, and the unstructured mesh benchmark. Each of these benchmarks incorporates a different type or different combination of types of non-determinism that are common and representative among the expanse of MPI applications. The message race benchmark includes the receiver-side non-determinism. The AMD 2013 benchmark adds onto this with sender-side non-determinism. And finally, the unstructured mesh benchmark adds onto both of these with the process topology non-determinism. Some more details on each of these can also be found in the publication listed at the bottom of the slide. Today, we're going to focus on one of these, the message race communication pattern. So here, to outline what the message race pattern is, we show 2 runs of the message race pattern. In each run, there are 5 MPI processes, where 4 of the processes each use MPI send to send a message to their 5th MPI process, which receives all of them, all the messages using MPI receive. In this particular configuration, we fix 2 of the messages to always arrive in the same order. Specifically, because those receives arrive in the same order, we say that it is deterministic. The other 2 messages are allowed to arrive in any order. And so those 2 receives are called non-deterministic. This measurement of half non-determinism and half deterministic corresponds then to a configuration of 50% non-determinism. By varying this configuration, we can see then that kernel distance acts as a proxy for non-determinism. To show this, we perform a test. And in this test, we use the following settings on the left of this slide. We use messages sent at the size of 1 byte. The simulation is done on a scale of 64 MPI processes with 2 compute nodes. And we run the message race pattern in 10 iterations for each of these runs. And then on top of these settings, for a sample space of data, we run the pattern 15 times. We also run these settings on the Stampede2 cluster computer with GCC 9.1.0 and Vapid 2 2.3.5. Finally, on the right of the slide, we visualize this, where at each setting of the percentage of non-determinism, we calculate the kernel distance between the graphs for each run at that setting. Now see, as the percentage of message non-determinism increases, so does the kernel distance. And this accurate positive correlation shows that Anacin-X can use kernel distance as an accurate proxy for the amount of non-determinism in the application. As we continue to improve Anacin-X, we're going to extend it to support a broader range of communication patterns, specifically those like collective patterns and one-sided MPI communication patterns. We're also going to use Anacin-X to evaluate the root sources of non-determinism for other applications, such as applications in cosmology and in molecular dynamics. Thank you for coming and for listening to our talk.